Okay, so welcome back to the DB2 course. It's time now to switch from PostgreSQL to MonetDB. And we will stick with the ProQuery Q1 because it's also interesting if we submit it to the MonetDB database system. Recall that MonetDB is the other database system that's primarily focused on operating in RAM, and we will see what consequences are taken in MonetDB to operate with this different medium of storage. The consequences are subtle and quite interesting, I would say. But let's first recall our first probe query, the Q1 query. It was super simple. It just retrieves all rows out of table unary, and it retrieves all the columns from these rows. Recall that this is a unary table. There's only one column A in this particular case. Later on, we will of course create wider tables, but for now, it's the unary table, and the only column A carries int values. Okay, so far everything as usual, but now we are switching from PostgreSQL, from the disk-based system, to MonetDB, to the primarily RAM-based system. How does MonetDB cope with this query Q1? First off, we can talk just regular SQL to MonetDB. MonetDB is a relational SQL-based database system, so we can use familiar commands to generate the table unary and its column A of type integer, and we can use familiar means to populate the table with 100 values. You see that there are some minor subtle differences in how we use generate series, the value, the sequence generator that we've already used in the PostgreSQL case. We can provide a start and an ending value. Actually, we have to increase this ending value by 1 because generate series will stop just before that ending value. So to generate 1 to 100, this is the parameters we have to use. We want to use a step width of 1, which would be the default. Note that there is some funny casting going on here, but let's not look at these particular details now. This is just a general generate series call as we have been using it in the PostgreSQL case also. Okay, so yeah, let's switch over. Let's switch over to MonetDB. So that's how the situation looks like now. We will start to talk SQL, familiar SQL commands, but we will send them to a MonetDB instance. Here you can see that I've already started the command line client, the M client of MonetDB, which is the replacement of the PSQL command line shell of PostgreSQL. And you can see that I've configured this shell, this command line shell of MonetDB, to talk the MonetDB SQL dialect. We will talk a different dialect in due course. Okay, so but let's just create this unary table. Okay, send these commands over. Okay, create it. Then populate the table as we have described. The default step width is 1, so that should work out fine. Okay, so 100 rows have been affected or have been inserted in this particular case. Looks good to me. Let's check the contents of this table. Familiar SQL here in this case. Let's check that. Okay, so 100 tuples, 100 rows are being output, and the table contents look like we are expecting it. Let's scroll upwards to the schema. Okay, column A, single column A, unary table. Everything looks good to me. Okay, so we are all set up. So now for the X-ray part, how would MonetDB handle the probe query Q1? What would explain tell us when it comes to the explanation for query Q1? And as you can see here on the slide, this already looks a bit different to what we've seen before. In PostgreSQL, of course, we were seeing this this sequential scan operation. This looks different to me. It actually, I've placed some dots here. Most of the plan I have actually omitted. So let's switch over to the shell again and look at the entire plan to get a feeling of what MonetDB internally performs when it evaluates this particular query. This is the probe query Q1. We are just appending or prefixing the explain keyword here in this case. Let's check again. Okay, all right. So this is the explain output. Lots of stuff here, but the interesting stuff is here in the beginning. A function is generated under the heading mal. A function is generated, and that looks like a sequential program to me. These are assignments to variables. So x1 is a void variable being assigned this value. x19 is a value of type but, I guess, assigned this value, and so on and so on. So it's just a sequence of assignments. That's the linear program. Going from top to bottom, that's a linear program, assigning values to variables that are then reused in later statements, so to say. That's a program. A program has been created, and a program is the internal representation of such a SQL query in MonetDB. Let's look a bit closer at that. The query plan that we are looking at indeed is a program. It's a so-called mal program. So the language in which this program is formulated is called mal, or the MonetDB assembly language program. Looking at these programs, you will see that these are mostly linear programs, evaluated from top to bottom. From top to bottom here is evaluating the expressions here on the right-hand side and assigning their values to variables, which may then be reused later on. You will find that no variable is assigned twice in these programs. That's the so-called single static assignment form, or SSA, which makes these programs particularly simple to analyze and to optimize. Okay, so a query plan is in fact a MonetDB assembly language program, just a sequence of such assignment statements. And internally, in fact, the MonetDB kernel implements a mal virtual machine. That's how MonetDB is internally constructed. A closer look at these mal programs. So you have seen that all the variables on the left-hand side of these assignment statements have been assigned an explicit type. And there's a number of types that we can use in mal programs. There's a number of so-called scalar data types, or as the mal MonetDB folks would call them, atoms. Okay, so these are the available scalar or atom types in MonetDB. We have bit variables, so these can actually only be assigned the truth values 0 or 1. That would be one way to write such a bit value. 1:bit would tell us that this is not a regular integer one, but it's supposed to be a bit value. Okay, so bits. Then integers of different width, bytes, shorts, integers, long, and huge integers. As you can see, these correspond from 8 to 128-bit integer values. Just writing 42 in such a mal program would assign the type int to that. That's the meaning of this underline here. But I can always be very explicit and just write a colon here and then append the atom type. For example, long in this particular case would make this 42 a 64-bit value, a 64-bit long value. Okay, then there's a particular type of OIDs. Looks like integers with this suffix @0 assigned. These OIDs will occur again and again. They are used in MonetDB, as offsets, as pointers into tables to quickly locate particular rows and tables. We will come back to that. There are float and doubles, so floating point values of different width, and there are of course strings. These are variable length strings. In mal they are put in double quotes, and they are actually encoded in UTF-8. Additionally, each of these scalar types has a nil value. A nil value is similar to the null value in SQL. It's not quite the same thing, but it's very similar. And I have, of course, nil values of the different types. I can again append a colon and a tau here, the type tau. Okay, so these are the atoms, the scalar values I can manipulate in a mul program. And then there's only actually one other type in these mul programs, and that's the so-called columns or BATs, binary association tables. Okay, this is the only one collection type implemented by MonetDB. These BATs are also assigned a particular type tau. Okay, and these taus will normally be atom types or scalar data types. So a binary association table can hold atoms of this particular type tau. Here's a depiction of such a binary association table. The binary in the name corresponds with the fact that such a table always has two columns. There are no 3-column tables, 4-column tables in MonetDB. These binary association tables always have 2 columns, and these are always called head and tail. This is the internal representation. Of course, I can have wider SQL tables in MonetDB, but internally they are represented by these BATs. Think of these BATs as the replacement for the heap files in PostgreSQL. This is the internal storage and data structure that MonetDB uses to store its data. In the tail column of these BATs, you find the actual payload that has been stored in this table, the actual integer values of this course. So we know that in this case, in this case, tau is int. In the first column, in the head column, you find such offsets or such OID values, which tell us that the 42 is actually stored at offset 0, the -1 is actually stored at offset 3. So the head column is an offset indicator that we can use to locate a particular row in such a BAT. Okay, because these offsets are really densely ascending, 0, 1, 2, 3, 4, it actually makes no sense to really physically store them. As long as we know that the first offset of this very first row has been assigned 0, the OID 0, it's clear that the next row will have 1, the next row will have 2, and so on. We don't actually have to store these values. That's why I have the head column with depicted with the dashed outline here. This is not actually stored. All that is stored is actually this column of tail values, the actual payload. All we have to remember for the head column that the very first offset is 0. All other offsets are densely ascending and will just follow this first offset 0. So the head column is fully virtual. It's virtual OIDs or VOIDs or voids, sometimes called in a MonetDB system. Only the tail column is actually stored inside RAM for us. And this is an ordered representation. It makes sense to speak of this particular row as the first row at offset 0. That would be the last row at offset 4 carrying a nil value here in this particular case. Okay, so this is an ordered representation inside the internal data structure, inside these BATs. We can actually sensibly talk of order. Okay, and MonetDB will make good use of that we're actually talking about an ordered array of values here, or maybe we could call it a vector of values. Okay, so I think it's time to play with these BATs and really create some of them and have the system operate over them and then see how the system reacts. So let's switch back to our terminal here. Okay, I'm quitting the SQL console that we were talking to MonetDB, and I will open a new console here. and it will be a mul console. Okay. Oh no, that's the wrong console. I'm sorry about that. Mul. There you go. All right, perfect. You see, that's a MonetDB interactive terminal. It's not a MonetDB/SQL interactive terminal. We can now really talk mul to the system. You can also see the prompt has changed from SQL to MSQL or mul and SQL. We will talk mul commands now at this particular prompt. So let's do that. Let's create a new empty but, a but of integer values. And I can use this but new function in mul for that. The new empty integer but will be assigned to mul variable t, and I can use later use that variable t to operate on that but, to query it, to modify it, and so on. So let's do that. Okay, so there is mul variable t created. Okay, so let's populate the but. Let's bring it into the state that has been actually shown on slides, carrying 5 rows. And we'll use a bet append command for that. So this is the payload we will be assigning or appending to the but t. Okay, so appending these 2 rows, 3, 4, 5 rows. Let's append 5 rows. The last row will carry the payload nil of type integer. Let's do that. Okay, so 5 append commands. We now expect 5 rows to be carried in this particular but. We can use the ioprint command in mul to check for that. So let's do that. Oh, there you go. This is the picture we have already seen on the slides. So it's 5 rows and they have these particular OIDs been assigned. Actually, this is the head column of type void. It's not actually stored, it's just printed here for our convenience. This is the payload, the tail column, the T column in this particular case, and it carries the actual payload that has just been assigned. So now to see that we can actually have positional access based on these offsets, based on these OIDs, let's use some other mul commands. For example, the algebra fetch command will look up in table T at offset 3, and at offset 3 we should find the -1, I guess. So let's do that. And then print the contents of variable v, and we will find the -1 as expected. Okay, so positional access based on the OID values inside buts. We will also use these offset values to replace the content of a particular row in a but. So inside but t, we at offset 4, we will now store 2. Formerly, there has been nil at this particular offset. After the sequence of these 2 commands, we will see that the but has changed its contents and the nil has been replaced by 2. Looks good to me. Okay, so positional update. Also positional slicing. So we can extract a sub-but from an existing but by providing a first and last row that we want to extract, that we want to slice out of the original but. So from but t, from these, between these 2 row offsets, slice all rows and assign them to a new but that will be the but t1. It will be, of course, also an integer but. So this will be the slice that we are going to extract. Let's do that. Okay, that's the new but t1. Of course, it has 3 rows now, starting at the offset 1, 2, 3. These are the actually not stored OID values, the offset values that have been assigned to these rows. As you can see in the new but t1, the offsets start at OID 1. In the original but, the offsets were starting at OID 0. And actually, such buts take care and take note of the very first offsets. We can also check that. We can use the but get sequence base operation in mul to look at to retrieve the very first OID offset that is assigned to the very first row in these particular buts. Let's check this for the but t and also for the but t1 at once. We can do that. Okay, yeah. So the first OID offset in but t is 0 and in t1 in the slice but it's 1, as expected. Looks good to me. Okay. How about deletions? How is free space managed in such a but? So looking at but t, the original but again, this is the original but again. So I want to delete the contents of the row at offset 1. You see, this is the OID I'm providing here as an argument. So let's see what happened. Will a hole be created? What is the state of the but after I delete the row at offset 1? Let's check that. Oh no, no holes are created. This is still a dense sequence of OID values. It always is. There is no way around this. The head column also always carries dense OID values. And as you can see, the formerly last value 2 here, the formerly last value 2 has been moved up to fill up the hole that's been created with the but delete command. The 2 has been moved up, and we have now a 4-row but still with a densely ascending OID column here in the head. It's a virtual column that's not actually stored. All that is stored is the payload that we are carrying here in the tail column. Okay, that's a first impression of what buts are and how these buts operate. And this will be the primary data structure, the data structure that MonetDB uses to store all its data. And it's quite different already from the heap files that we have introduced for PostgreSQL. That promises a very interesting comparison in discussion in the upcoming course videos. And until then, take care, bye-bye.